Good day, I'm Norman Wahlberger. In today's lecture, we're going to be looking at a very core formula in set theory, usually called the principle of inclusion-exclusion. And it's telling us something about sizes of unions and relating that to sizes of sets and intersections. The simplest example is when we have two sets, A and B. And the usual picture or Venn diagram that goes with it is something like this. So here this circle represents the set A, this circle represents the set B. This area in between here in red is representing the intersection of the two sets, and the collection of all of the green area represents the union. Okay, and the principle of inclusion-exclusion for these two sets A and B is usually stated this way, that the number of elements, or the size of A union B, is the sum of the size of A plus the size of B minus the size of the intersection A intersect B. Now this result generalizes in a natural way to more than two sets, to in fact n sets, and it's really a core result in modern set theory. So we're going to be looking at this result, but definitely with new eyes in this video. So we're going to learn, first of all, an extension of this theorem where the emphasis is not with sets but rather with multisets, and we're actually going to understand this theorem in a fundamentally new kind of way. Here is what the principle or theorem looks like for three sets A, B, and C, where the Venn diagram looks something like this. So the statement is that the size of A union B union C, in other words, the size of the whole conglomeration where we put everything together, is equal to the sum of the size of A plus the size of B plus the size of C. And then we have to subtract the sizes of the three intersections. The size of A intersect B, which would be that area there. The size of A intersect C, which would be that area there. And B intersects C, which would be that area there. But then in addition, we have to add the size of the common intersection A intersect B intersect C, which is represented by this little area here that's common to all three sets. So it's kind of an alternating aspect. We take the sum of these three, and then we subtract the sizes of those three, and then we add the size of that yet smaller intersection. So we're going to see that this formula, common, and in fact very standard and very fundamental and useful though it may be, is actually but a shadow of a more fundamental result. And that more fundamental result really becomes mostly visible to us in the realm of integral, or maybe even rational multisets. So we have to expand our thinking in two very distinct directions. We have to go from sets to multisets, and we have to enlarge our view to something called integral multisets. And it will turn out that what we say for integral multisets will also extend to rational multisets, but we'll talk about that some other time. To give an example of the inclusion-exclusion theorem or principle, here is an application from number theory that has to do with Euler's phi function, sometimes called the totient function. This is a very important function in number theory. So if n is a natural number, phi of n is the number of numbers less than or equal to n, which are relatively prime to n. So we're counting the number of elements in this set M, such that M is between 1 and n. M is also a natural number. And M and n have no common factor. That's represented by the symbol that means that they're relatively prime. So for example, phi of 6 is 2 because there are two numbers, namely 1 and 5, which are relatively prime to 6, in the range 1 to 6. Phi of 7 is 6 because there are 6 numbers relatively prime to 7, namely 1, 2, 3, 4, 5, and 6. And phi of 8 is 4 because there are 4 numbers relatively prime to 8. It's not hard to see that if p is a prime, then well, all of the numbers up to p minus 1 are going to be relatively prime to it. So phi of p is in that case p minus 1. And if P and Q are both primes, distinct primes, then phi of P times Q is P minus 1 times Q minus 1. So this phi function has a kind of a multiplicative aspect, at least when the two numbers here are relatively prime. Okay, so to understand why this is true is a nice little exercise that sort of illustrates the basic idea of inclusion, exclusion. So here's just a sort of a diagrammatic idea of the proof. You can think about it. So let's make a box, and let's let this box represent all the numbers from 1 to the product P times Q. So all of the numbers are in there. And now inside that box we're going to identify two sets. First of all, A, which is the set of multiples of P, and B, this one over here, which will be the set of multiples of Q. So inside the numbers from 1 to P times Q, there are multiples of P, namely P, 2P, 3P, all the way up to Q times P. So the number of elements in A is Q, from 1 times P all the way up to Q times P. And similarly, the multiples of Q range from Q to 2Q to 3Q all the way to P times Q. There are then P of them, so the size of B is P. And what about the common intersection between those two sets? Which numbers are multiples of both P and Q in this range? Well, P and Q are primes. There's only one such number, namely P times Q itself. Okay, so what would inclusion, exclusion tell us about the union of A and B? It would tell us that the size of that union is the number of elements in A, which is Q, plus the number of elements in B, which is P, minus the number of elements in the intersection, which is just 1. So we would have P plus Q minus 1 is the size of that union. And those are the numbers which are either multiples of P or multiples of Q. And so if we want phi of P times Q, we want to count all the numbers which are not having a common factor of P or Q with P times Q. In other words, we want to take P times Q minus this union. So P times Q minus the union P plus Q minus 1 turns out to be P times Q minus Q plus 1, which is this expression here. So inclusion, exclusion plays a natural and actually important role in this kind of number theoretical situation where we're counting multiples and common divisors and things like that. So this inclusion, exclusion principle is all well and good, but we want to go further and we want to understand it in a bigger kind of way. And in order to do that, I want to a little bit more formally introduce this idea of integral Msets, which I have talked about a little bit informally, but I want to be a little bit more precise or say a little bit more about that. Okay? So let's remind ourselves that if, say, M is an M-set from 5, what that means is that M is a K-M set from 5 for some K, a natural number plus, in other words, a number of the form 0, 1, 2, etc. In other words, for example, we're talking about an M-set whose elements are all taken from 1 through 5. And there might be 0 elements, in which case we have the empty M-set, or there could be, in this case, 1, 2, 3, 4, 5, 6, 7, 8 elements, or there could be 3,000 elements. Okay, there's no real limit on the number of elements if we're talking about M-set 5, but all of the elements actually have to be between 1 and 5. Okay, so that's the kind of object we're thinking about momentarily. And we've seen that this kind of M-set can also be written in an alternative way using our algebraic properties of M-sets. The fact that we can add M-sets, that we can multiply an M-set by a constant. So we can rewrite this as 2 times the mset 1, representing those two ones, plus the mset 3, plus 2 times the mset 4, plus 3 times the mset 5. So this is a way of sort of bringing the objects together, kind of organizing the mset a little bit more efficiently. And we've seen that once we've gone to that stage, we can kind of go one step further and create a new object which just records the various multiplicities of the various objects 1 through 5. So the possible elements that occur in this mset are 1, 2, 3, 4, 5, and we can record an mset by recording the multiplicities that each one of those elements actually has in the given mset. And we could maybe call this the list of m. Let's use the word L, because it actually is a list. So L of m, in this case, is the list 2, 0, 1, 2, 3. That records the fact that we have 2 1s, 0 2s, 1 3, 2 4s, and 3 5s. So this list is a list of multiplicities of the fundamental numbers 1 through 5 in the given mset m. And I remind you, this is our notation for multiplicity. So we say that the multiplicity of 5 in m, or m sub m of 5, is 3. That 3 there represents the fact that there are 3 5s in our mset. Okay, so now we note that the entries of this list, these are general numbers, natural numbers, in that plus. So they could be natural numbers or possibly 0. And these are just the multiplicities of these various elements, these numbers L, as L ranges from 1 to 5. So to an mset, we can associate a list. And the list has entries which are natural numbers or possibly 0. And you may remember in a few videos ago when we were talking about this, that sort of opened up the possibility for us of maybe being a little bit more general and thinking about more general kinds of objects where we allow these multiplicities to be also negative numbers, integers. That's a very interesting kind of enlargement of our point of view. To summarize what we've just done, we started with the mset capital M, which was an mset from 5, and to it we associated a list. In fact, it was a 5 list, whose entries were natural numbers or natural numbers including 0. So now we want to extend the notion of mset to what we might call an integral mset. And I want to write this in a somewhat novel way with the sort of underline bar here, as one does when one is, say, typing in a name of a file or something on your computer system, and you don't want to leave a space. You want to connect this word with this word, so we use one of these sort of underscores. So I'm going to do that to suggest to you that the integral is not an adjective applied to mset. So we're not talking about looking at msets and then inside msets finding particular things called integral msets. What we're doing is rather going the other direction, where we have the notion of mset and now we want to enlarge the notion of an mset to an integral mset. So this is a bigger notion, not a smaller notion. So the idea is we're going to let the multiplicities of elements in these integral msets be integers, not just natural numbers including 0. We're going to allow the multiplicities of elements to be also negative numbers, so in general integers. This is going to give us a new type of object, which we're going to write, say, as int mset n. So in this case, this means integral mset from n, where the elements of the mset are still one of the numbers 1, 2, up to n. But now all the multiplicities are allowed to be integers. possibly natural numbers, possibly 0, possibly negative numbers like -3 or -27. For example, here, this set M, this Mset M, actually this integral Mset M, is given by the square brackets, and then there are these elements here. And we're going to adopt the convention that if we have an element in brackets, it means that it's occurring with negative multiplicity. So this is an int Mset from 5 because the elements are all either 1, 2, 3, 4, 5. And 1 occurs with multiplicity 1. 5 occurs with multiplicity 2. 2 occurs with multiplicity 2. The number 3 occurs with multiplicity 0. But the number 4 occurs with multiplicity -3. Right? So we're kind of using a counting notation where that bracket means that that 4 is actually a debt, not an asset. It's to be counted negatively. We could also maybe have written it in red, but we'll just stick with this bracket notation. Right, so this means these things here are all negative multiplicities. And so the associated list of multiplicities would be, well, there's 1, 1, there's 2 2s, there's 0 3s, and there are -3 4s. There they are there. There's -3 of them. And there are 2 5s. So it's just as before, we end up with a list, but now the elements of the list can be integers, not just natural numbers or 0. So we're extending our view to so-called integral Msets. We're broadening our vision. Now you might well say, well, this doesn't make any sense. You know, what does it mean to have -3 4s? Well, this is the same kind of dilemma that 16th century mathematicians like Descartes felt about negative numbers. What does it mean to have -3 cows? What does that mean? Is -3 really a number? People debated this, and in fact, they were in many situations reluctant to accept numbers like -3 or -5 or -3 halves as legitimate solutions to equations. They wanted to separate the positive numbers, which really made sense, with these negative numbers, which were sort of artificial constructs. These days, students are taught to have a more sort of wide, accepting, tolerant view of negative numbers, and mathematicians generally often think of negative numbers and positive numbers as really just two sides of the same coin. One is not better than the other. They have equal sort of merit. But that's a relatively modern concept. And what we're doing here is really pushing that concept into the realm of data structures. Saying, well, if we're going to talk about the negative number -3, and we're willing to admit that there might be something like -3 cows, then we might as well allow data collections in which -3 cows figure. We have 2 horses, 7 pigs, and -3 cows on our farm. Okay, maybe there's some sense to that, right? That's what we're doing here. Okay, so we can now extend our algebra of multisets to these integral Msets. And in particular, not only do we have addition, union, and intersection, as we already have talked about quite a lot, but we now also have subtraction. This is the beauty of having integers. This is what having integers does for you, is that you can systematically subtract. You can not just subtract like 5 minus 3, but you can also subtract 5 minus 27. That doesn't bother you. You don't have to fuss around about whether the numbers are in the right range. You can always subtract. So similarly, now we're in a position of being able to subtract Msets if we're in this realm of integral Msets. And that's exactly what we're going to need for the inclusion-exclusion theorem. Okay, so let's remind ourselves sort of how the story goes. So addition of sets, remember that just means we're sort of putting everything together. And we're basically adding multiplicities of any elements. So if we have the Mset 3 and 1 with negative multiplicity, 1 with negative multiplicity, and 4, and then here's another Mset 2 1, and 4 with negative multiplicity. If we put those all together, then altogether we have a single 3, we have a single 2. How many 1s do we have? Well, we had minus 2 1s here, and we had 1 1 there. That gives us a total of minus 1 1. There's the minus 1 1 in the sum. And how many 4s do we have altogether? Well, here we had 1 4, and here we have minus 1 4. When we add those, the multiplicities add. So we have 0 4s altogether, so there are no more 4s in the sum. How about union? If we take the same two Msets and we take their union, then we're taking the maximum of the multiplicities for each of the elements. So how many 3s are there? There's 1 3 here and no 3s there. The maximum is a single 3. How many 2s are there? There's a 2 here and none there. There's a single 2 in the maximum, or the union. Here we have minus 2 1s, and here we have 1 1. The maximum of those is 1 1. Here we have a 4, and here we have a minus 4. The maximum of that is 4, or a multiplicity of 1. So we have a single 4 in the union. Intersection is the same story, except now we're taking the minimum of all the multiplicities. So there's a 3 here, but no 3 there, so the minimum of that is 0, so there's no 3 in the result. There's a 2 here, but no 2 there, so the minimum is 0, so there's no 2 in the result. There's minus 2 1s and 1 1 over here. The minimum of that is minus 2, so there'll be minus 2 1s in the intersection. And the minimum of 1 4 and minus 1 4 is minus 1 4, so there'll be minus 1 4 in the intersection. And now finally, our new operation that we couldn't do before, we can now subtract in a kind of an honest way, not that sort of partial subtraction that we considered before, but really a genuine subtraction of Msets is now possible in this realm. So 3, 1 negatively, and 4, subtract 2, 1, and 4 negatively, gives us what? Well, there's a 3. There's now going to be minus 3 1s, because there's minus 2 of them here, and then we're subtracting another one, so that's a total of minus 3. How many 4s? Well, there's 1 4 here, and there's minus 1 4 there. So if we take 1 4 and we subtract minus 1, we get 2 4s. So we have 2 4s in the final result. And there's 0 2s here and 1 2 there, so when we subtract, we get a negative 2. So at the level of individual elements, these operations correspond exactly to just addition, union, intersection, and subtraction of multiplicities. If we just focus on, say, the 3s, then each one of these operations just corresponds to either adding the numbers of 3s, or taking their union, or taking their intersection, or taking their differences. So it's a wider, more flexible arithmetic that we gain by introducing these integral Msets. Exactly the same kind of advantage that we have when we introduce integers into ordinary arithmetic. We can then do subtraction more uniformly. Okay, so now we can state the inclusion-exclusion theorem. And notice that I'm not going to call it the principle of inclusion-exclusion. My experience is that when we're talking about principles, there's often some confusion or ambiguity not far away. So principle is a kind of a word that people use when they're not really sure about something and they have to kind of pull the wool over somebody's eyes, perhaps their own eyes, and they like to use the word principle to make this a little bit more palatable. So this is not a principle, this is a theorem. It's just a theorem like any other theorem. And here is actually the theorem in a more wider and more powerful context than it's usually found. So this theorem is found in many texts, but I think one could make the case that this is actually sort of really the correct way of thinking about it. And it's probably a novel formulation, so it may be in fact the first time where this theorem has actually been stated correctly. It's interesting. Okay, so what is our formulation of this? So let's let n be a natural number. And suppose that we have integral msets from n. So we're not talking about general sets or msets. We're being specific like we like to be. So all of our elements or entries are going to be from 1 to n. We fix that. We have very definite bound. We know exactly what range we're talking about. Okay, so we've got these k integral msets from n. Capital M1, capital M2, up to capital Mk. Okay, so here is then the statement. The statement is that M1 union M2 union up to union Mk. So this is the union of these k integral msets. That's going to be another integral mset. So that integral mset is the same as the integral mset that's represented by this long right-hand side. So let's have a look what that is. There's a number of different components to it. The first is the sum of just the integral msets, m1 plus m2 all the way up to mk. So we have to add those all up as integral msets. We've just been talking about how to add integral msets. We know how to do that. That's what we're doing here. And now we're going to subtract some other integral msets in the context of algebra of integral msets. We've just established that we're able to subtract. Okay, that's exactly what we're doing here. We're subtracting msets. So this is the mset m1 intersect m2, m1 intersect m3, all the way up to, and we're going to take all possible combinations of two distinct msets or integral msets in this range. So all the way up to mk minus 1 intersect mk. And each one of those has a negative sign in front of it. Then we switch to triples of msets and their intersections. So m1 intersect m2 intersect m3. That's one triple. Then m1 intersect m2 intersect m4. That's another triple. We go through all the distinct triples up to the last one, which is, say, mk minus 2 intersect mk minus 1 intersect mk. And each one of those intersections of three msets has a plus sign in front of it. And then we carry on. So at the next step, we're going to do subtraction, and we're going to subtract all four tuples of distinct msets. And then we're going to add all five tuples of msets, and so on, until eventually the last stage, we're going to have the intersection of all k of them. So the final thing will be m1 intersect m2 all the way up to intersect mk, and that will either have a minus 1 or a plus 1 in front of it, depending on whether k is even or odd, because it alternates even, odd, and so on. So let's have a look at what that actually looks like concretely when k is 4, where we can write down everything rather concretely and we can see all of the terms. So if k is 4, then the left-hand side is m1 union m2 union m3 union m4, and then we have the sum of the m's, and then we subtract all the various intersections. m1 intersect m2, m1 intersect m3, m1 intersect m4, m2 intersect m3, m2 intersect m4, and m3 intersect m4. Those are all the possible ways of, picking 2 out of the 4. And then we're going to add the various triple intersections. So m1 intersect m2 intersect m3, plus m1 intersect m2 intersect m4, plus m1 intersect m3 intersect m4, plus m2 intersect m3 intersect m4. And finally, we're going to subtract the intersection of all 4 of them, m1 intersect m2 intersect m3 intersect m4. So this is a statement about integral msets. The left-hand side is an integral mset. The right-hand side is an integral mset, composed of adding and subtracting lots of integral msets. And that's the statement of the theorem. It's a theorem about algebra involving integral msets. So how are we going to establish this theorem? Well, the key observation is to recognize that the proof is really a direct consequence of the corresponding fact about integers. Because the multiset operations correspond exactly to the operations on multiplicities. In other words, we can look at what's happening one element at a time. If all of our elements are from the range 1 through n, then it suffices to establish the result by the corresponding sort of formula for each element separately. Multiplicities of 1, multiplicities of 2, all the way up to multiplicities of n. So there's a corresponding inclusion-exclusion theorem for integers, which is logically prior to the one for Msets. The one for Msets really comes down to this corresponding fact about integers. And the statement for integers is really pretty well exactly the same, but I've taken the liberty of giving you a different way of writing it, because it's often we have this sort of summation notation, so it's good to have some experience in rewriting what we've done using the summation notation. So for integers, suppose we have k integers, m1, m2, up to mk. So these are little m's representing the fact that they're integers. So the statement is then that the union of these mi's, so m1 union m2 all the way up to union mk, and that's represented by this expression. So there's a union sign, and underneath there's the expression 1 less than or equal to I less than or equal to k. So k is fixed, so I is running from 1 through k, and we're taking the union of the mi. That's the way of writing m1 union m2 union dot 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 union mk. And then on the right-hand side, the first term is the sum of all the mi's. So that's just the sum as I goes from 1 to k of mi. And then the next term, we can write it as with a minus sign, and then the sum as I and j range from 1 to k, and I is always less than j. So that guarantees that we're picking out all pairs of distinct elements from 1 to k. And for each one of those choices of indices, we have a corresponding intersection of the numbers mi and mj. Mi intersect mj. And then the next term is a sum, so it alternates plus, minus, plus, so here's the next to plus. And now we have to take sums of things like look like this, mi intersect mj intersect ml, and we agree that the indices I, j, and l have to all be distinct, so we arrange that by having I less than j less than l, and all three of them go from 1 up to k. Okay, and then we carry on like that, alternating in sign, taking more and more elements in the intersections, until finally, this should be minus 1 to the k. Then, actually this is the second last term. Let me that a little bit neater. So there's a minus 1 to the k. So the second last term we have k minus 1 elements. So we can write that as mi sub 1 intersect mi sub 2 intersect all the way up to intersect mi sub k minus 1. So because there's k minus 1, I don't want to use I, j, l, because I have to keep using new letters. So now I'm sort of changing our notation for the labels or the indices. Instead of I, j, and l, we're using I sub 1, I sub 2, all the way up to I sub k minus 1. And these indices have to have the property that they're distinct. So we may as well arrange that I sub 1 is less than I sub 2, is less than all the way up to less than I sub k minus 1. And all of them have to be in the range between 1 and k. And then finally, the very last term is where we have all of the mi's, m1 intersect m2 all the way up to mk, and that's got a minus 1 to the k plus 1. So the inclusion-exclusion theorem for integral msets is a consequence of this formula for integers. This is really an arithmetical formula. It's a formula of arithmetic. So let's see how we can prove the result for integers. And let's start by understanding what happens when k equals 4, when we can be very explicit. So by symmetry, let's assume that we have these 4 integers, m1, m2, m3, m4. And since everything is symmetrical, let's arrange that they're actually in increasing order. So m1 is less than or equal to m2, less than or equal to m3, less than or equal to m4. Some of them could be equal to each other, but they're at least sort of increasing. So here's the equation that we're trying to prove. So this is the k equals 4 version. So here's the union of all 4, the sum of all 4, and then here we have the subtraction of all the various pairs of intersections, and then we have the sum of the various triples of intersection, and then we have the difference, subtract again, the intersection of all 4 of them. So we want to prove that this is an identity that's valid for all integers m1, m2, m3, m4, and we may as well arrange that they have that relation. All right, so let's ask ourselves, how many times is m4 going to occur on both sides? In other words, when we evaluate these various intersections and unions, how many of them are going to be actually equal to m4? And let's agree that when we have something like intersection of m3 and m4, that's the minimum of m3 and m4, that the minimum of these two things is always going to be stated to be m3. Even if potentially these are equal, they could be equal, but nevertheless we're going to adopt the convention that when we write m3 intersect m4, we always take the minimum. That's equal to m3. That's a true statement. So how many times is m4 going to appear here? Well, this thing here represents the maximum of these 4 numbers, and m4 is the maximum by agreement. So m4 does actually equal this. So when we evaluate this thing, we're going to get m4. So there's an m4 appearing once on the left-hand side. And the m4 appears also right there. Does it appear in any of these other terms? No, it doesn't, because each one of these is an intersection, meaning a minimum. Intersection of 2, intersection of 3, intersection of 4, and m4 is the biggest one, so the intersection of the minimum is never going to be m4 for all of these terms. So there's one m4 that occurs on the left-hand side, and there's exactly one m4 that occurs on the right-hand side, and that's all. Now let's look about what happens with m3. So m3 occurs not at all on the left-hand side, because that's only m4. m3 occurs once there. And how many of these other intersections are equal to m3? Well, m3 is the second biggest one, and that's going to occur as a minimum only when we take m3 intersect m4. So it's going to occur right there. This particular intersection will evaluate to m3, but none of the other ones will. So the total number of times that m3 occurs on the right-hand side is 1 minus 1. So it occurs 1 minus 1 times on the right-hand side, which is, of course, 0. So the m3s occur with the same number of times on each side, namely 0. How about the m2s? m2 occurs 0 times on the left. How many times does it occur on the right? It occurs once right there. And how many m2s are going to occur here? Well, m2 intersect m3, that's going to evaluate to m2, because m3 is bigger than or equal to m2. m2 intersect m4 is going to also evaluate to m2. So there's going to be 2 occurrences of m2 coming from these 2 terms. And here, of these terms, this one here will evaluate to m2, because m2 is indeed the minimum of these 3. And m2 is not going to appear here, because this evaluates to m1. So the number of m2s that appear on the right-hand side is 1 minus 2 plus 1, for a total of 0, which equals the number of m2s on the left-hand side. And finally, let's look at what happens with m1. There are 0 m1s on the left-hand side. In terms of m1s, there's 1 here, and there's an m1, there's an m1, there's an m1. There's 3 m1s appearing here with the negative sign, so there's minus 3 occurrences there. And in terms of these ones, that's an m1, because the m1 is the minimum of those 3. m1 is the minimum of those 3. m1 is the minimum of those 3. not here. So we have 3 m1s occurring corresponding to those terms, and they all have plus signs, so there's a plus 3. And finally, this last term, the minimum is m1. So m1 will occur there with a minus 1. So altogether on the right-hand side, the m1 occurs once, minus 3, plus 3, minus 1, for a total also of 0. And so the number of m1s on both sides is also equal to 0. So overall, we've sort of kept track of each one of these terms, how many times each one of them will appear, and we've seen that there's a complete balance, and so that the left-hand side actually does equal the right-hand side. This is an identity valid for all integers m1, m2, m3, m4, satisfying this relation. And that proves this identity for k equals 4. Well, what about the argument for k equals 5 or higher k, or arbitrary k? Well, it turns out that it's really just a generalization of this. You can kind of see, I hope, that here we really have binomial coefficients. We're really having the expansion of 1 minus 1 to the n. Yeah. And since 1 minus 1 to the n is 0 to the n, the story is going to be really the same. But I'd like to leave this to you as an exercise to think about, to convince yourself that this argument extends in a nice way to arbitrary k. And I suggest that you might like to look at what happens when k equals 5. So if you're wanting to clarify what's going on here, if you write down what happens with k equals 5, it'll become very clear to you what the pattern is, I hope, and then you'll be able to see that it generalizes to arbitrary k. So that's essentially the proof of the inclusion-exclusion theorem for integers, and that gives us then a proof for general integral Msets. I still need to connect our general formulation of inclusion-exclusion with the usual formulation in terms of sizes of sets. So to do that, let me just remind you a little bit about sizes. So for example, if M was a k M set from n, then we said that the size of M equals k. That's the size of M. So for example, if M is this M set here, then its size is 6. We just count the number of elements. And if here is the list of M, this is a different M set. It has 3 1s, 0 2s, 0 3s, 4 4s, and 2 5s. Then in this case, the size of M can be read off as a sum of the multiplicities. It's 9. And this notion of size has some pleasant properties. In particular, when we add 2 M sets, then the size of M plus n is equal to the size of M plus the size of n. And if we multiply an M set by a scalar or a number like n, if we multiply an M set by 2, I remind you that just means that we double all the elements. So the size of nm is n times the size of m. Now these notions extend to integral M sets. So for example, if we have M, the integral M set, 1, 1, 2, negative coefficient, 2 with a negative coefficient, 2 with a negative coefficient, 4 and 5, then the size of M is what? So we have to count how many elements it has. So each one of these contributes plus 1, and this contributes minus 1, minus 1, minus 1, and so on. So for a total of M has size of 1. At the level of the list, if we have an integral M set and its corresponding list is 0, minus 1, 4, minus 2, 8. So here this would represent a M set that has 0 1s. The number of 2s is minus 1. Number of 3s is 4. The number of 4s is minus 2. The number of 5s is 8. Well, in that case, the size of this is just the sum of all these multiplicities, which would be 12 minus 3, it's 9. So the notion of size, just the sum of the multiplicities, just as it usually is, works just as well for integral M sets. Now for integral M sets, since we're allowed to do subtraction, we have to augment our properties of size to the difference of sets. So if we have the difference between M sets M and M, the size of that is going to be the size of M minus the size of N. So now we can say that the usual inclusion-exclusion theorem, let's call it a theorem because that's what it is, not a principle, follows from the more general theorem. So here is the sort of usual formulation given in terms of sizes of sets, where the size of the union is equal to the sum of the sizes of the individual sets minus the sum of the sizes of the intersections plus the sum of the sizes of the triple intersections, and so on, all the way up to minus 1 to the k plus 1 of the size of the k-fold intersection. So this is then a direct consequence of the fact that the size function or size notion respects addition and subtraction. And it's then something that's was usually stated only in terms of sets. And you can see why it's stated this way in terms of sets, because in terms of sets, it doesn't make any sense to add sets. You fall outside of the realm of sets if you do that. And similarly, it doesn't make sense to subtract intersections. You can't do any of that in set theory. But that's a very limiting way of looking at things, as we've seen now. So I hope you now recognize this is just a shadow of the true inclusion-exclusion theorem, which is really about integral Msets, and is really making a statement about the algebra of Msets directly. In our next video, I'd like to expand on this sort of interesting role that Msets play. It's a very important message to try to get people to think more broadly, not just set theory, but Mset theory. Very important, bigger picture to have in mind. So we're going to have a look at some applications to number theory, including unique factorization and the relationship with prime numbers. Okay, so interesting applications of Mset ideas. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.